All right, here's another example. Here's some function f. Here's the domain over here, and here's the range. So we're taking 3 sample points, and we don't have an expression for f. You don't need an expression for f to define a function. I'm just telling you that f is a mapping that maps 0 to -5, it maps 4 to 7, and it also maps 5 to 7. Okay. Well, you might ask, well, okay, if f has an inverse, what's the inverse of 7? The way you find an inverse is like the black arrows and the red arrows. You follow the black arrow backwards. But here, 7, there's a problem. You've got 2 arrows coming into it, at least 2. So you don't know which arrow to follow. So in that case, actually, f has no inverse. The inverse of f is undefined. So not every function has an inverse. The reason this function does not have an inverse is because it takes 2 different inputs, maps them to the same output. In computer science, we call this a collision. Okay, these 2 inputs are colliding to the same output. If a function has a collision, it can't have an inverse. But if there are no collisions, then it does have an inverse, so it goes both ways. That should not be there. All right. Sorry. I'll erase those. So a function f is 1 to 1 if for every output there is only one corresponding input. So if look at the outputs of f. If every output only has one input, in other words, there are no collisions, then we say f is 1 to 1. So this f is not 1 to 1. In fact, it's at least 2 to 1, because I've got at least 2 points here that map to the same point. There might be more than 2, but it's 1 to 1 if every output there is only one input that maps to it. Okay. Another way of saying that is if I take 2 inputs that are distinct, so they're not equal, then the 2 outputs have to be distinct. This is just another way of saying that there are no collisions. So it turns out a function, this is a theorem you can prove, a function has an inverse if and only if it's 1 to 1. So it's the 1 to 1 functions that have inverses, the functions that don't have collisions. So let's do an example. Let's look at a squaring function, which we've seen before. Does this have an inverse? No. What do you think? Yeah, no. Right? Because you know it doesn't have an inverse because we're introducing it on the same slide that has this inverse. That's how you know. So the theorem says, well, it has an inverse if and only if it's 1 to 1. So is it 1 to 1? Again, the soft answer is no, it's not, because it's on this slide. But let's do an actual proof of that. So here's a counterexample. Here are 2 inputs, 2 and -2. If you square them both, you get 4. So their outputs are equal. The -2 squared is positive 4, and 2 squared is positive 4. So you have 2 distinct inputs colliding to the same output. There's a collision. This is not 1 to 1. Therefore, this function does not have an inverse. So the squaring function does not have an inverse. Graphically, here's what the squaring function looks like. It's a parabola facing up like that, going through the origin, going up on both sides. Okay. Here's x equals 2 on this side, and here's x equals -2 on this side. Notice that the y values are both 4. So the y values you get from these 2 distinct x values, when you hit the graph, they're on the same horizontal line, with the same y value for each. That gives us a graphical test to see if a function is 1 to 1. A function is 1 to 1 if and only if each horizontal line intersects the graph at most once. Here, this line, oops, I'll get to that. Here, notice that this graph, the squaring function, violates that. You draw a horizontal line, and this horizontal line intersects the graph at 2 points, 2 distinct points. So this fails the horizontal line test. So this function is not one-to-one. And you only have to find one line that intersects more than once. Okay. And it fails the test. All right. So a function is one-to-one if each horizontal line intersects the graph at most once. But here's a very important, so pay attention now because we're going to see this again. If you have a function that's not one-to-one because it's got some collisions, you can always artificially restrict the domain of the function so that it is one-to-one. And the way you restrict it is you just remove points that are colliding with other points. So that if you have a collision, you can say remove all but one of the points in the collision. And that gets rid of that collision. So just take them out of the domain. And so this is the reason why we sometimes actually have to specify what the domain is explicitly. We don't get it by default by looking at the expression. We will actually explicitly say, yeah, even though the expression makes sense for this point, it's not going to be in the domain of the function. So you can always restrict the domain to make it one-to-one. So here's the example for the squaring function. We're now going to restrict the function f of the squaring function to this domain, the non-negative reals. Okay, here's the graph. So notice this is not the same function. Very important. These are two different functions. One is a restriction of the other. This is restricted to just the non-negative reals, so it includes 0, but it only has the positive reals, not defined for the negative reals. So this only has one branch of the parabola, where this has both. Okay, so it's a different function. But notice this satisfies the horizontal line test. If you draw a horizontal line anywhere, it's going to intersect the graph at most once. It'll never intersect it twice. So in fact, what we've done is we've removed all the collisions by just taking out, by fiat, taking out all the negative inputs from the domain. Okay. So we are restricting the function to the positive numbers plus 0, including 0. All right, this function is one-to-one. So by the theorem on the previous slide, this function has an inverse. What's its inverse? Yeah, it's going to be the square root function. Okay. So the way you find the inverse graphically is you draw the line y equals x through the thing, and then you you flip the graph like a pancake through the line, and you get this thick black line. That's the graph of the square root function. So that's the punchline of the joke. Well, let's actually tell the joke. So to find the formula for f inverse, you can always do the following. So this recipe will always work, essentially. Look at the equation. Look at the expression for f of x, the defining equation for f applied to an arbitrary x. First, replace f of x with y. Swap x and y. Solve for y. Replace y, the letter y, with this expression, f inverse of x. And that gives you a defining equation for f inverse of x. So let's just step back and see this again step by step in this example here. Okay. So here's the first thing. F of x is equal to x squared. So the first thing we do is, in the equation for f of x, this thing right here, replace f of x with y. So just set y equals x squared. It's really, this is only for convenience, so we're just working with letters and not hauling a big expression around. Now, swap x and y. So everywhere you see a y, change it to an x, and everywhere you see an x, change it to a y. Again, this is not really necessary. It's only because our unnatural preference for using x as the input variable. So changing this to x is equal to y squared. Now we solve for y. Okay? So take this equation. How do you solve for y? What do you do? Take the square root of both sides. Okay? So you get that, well, also flipping sides here, you get that y is equal to the square root of x. Yeah, but this, when you take the square root of both sides, there's this problem that arises, right? What happens when you take the square root of both sides? You're really getting two solutions. There's the positive solution, and there's the negative solution. Okay, so going from here to here, we really should have put a plus or minus. Sorry, I need to step back to the camera. We really should have put a plus or minus right there. Okay, saying y could either be the positive square root of x or the negative square root of x. But we said it's just the positive square root of x and not the negative square root of x. Why is that? Here's why. Because of our domain restriction. We restricted the domain of f to be the positive reals, plus 0. Okay. So in this equation, we really should record that information. We should say that x is greater than or equal to 0. Okay. In that equation for y equals x squared. Because that is our restriction for the domain. So let's go to step 2. When we swap the roles of x and y, do it consistently over here as well. So, yeah, bless you. So the x gets changed to y. So now we have the restriction, our artificial restriction, that y has to be greater than or equal to 0. And that tells you that that has to be the positive square root of x. So the square root of anything, if it's well defined, is going to be positive or 0. Right? So the square root of something is not going to be negative. So because we know that y is greater than or equal to 0 here, because of our domain restriction, we don't have to say this. We can just say the positive branch of the square root function. Okay. If we did not have that domain restriction, then we'd have an ambiguity here. We'd have a collision, right? We'd have two values whose square gives you y. We have two values whose square gives you x. One, the negative of the other. But by restricting this domain, we've essentially removed removed that collision. And so y is going to be the positive square root of x. Okay. And now the final step is just replace y with the expression f inverse of x, and that gives you the defining equation for f inverse. Okay. Questions on that? All right. So there's a little more to it than what I have here. Sometimes you actually have to keep track of the domain restrictions. And the key point is, when you do a step, when you go, these steps should be reversible. In other words, you should be able to start with this equation and derive the one before it. And then this one derives the one before it. And this one derives the one before it. Okay? I'm sorry. Scratch what I just said. That doesn't apply in this case. That does apply in general. In this case, it's true. It's true automatically. There are some cases where you have to be careful about that. It's not true, and maybe in the next break I'll show you one of those. Okay. But this works in general as long as these steps are reversible. In this case, they are, and you can go forwards and backwards, and that'll actually give you the inverse. Do I have another example? Yeah, good. Okay, let's do another example. Take the same square root function, but now restrict it to the negative reals plus 0. So restricted to all the real numbers which are negative and 0. We might call those the non-positive reals. Does this have an inverse? Yes, it does. Because now, here's its graph. This function is different from the previous two. Now the branch is on the left side. So it is one-to-one. It passes the horizontal line test. So here's the graph. So to get the inverse, you reflect it in that line, and you get that thing. Okay. Notice that this looks like that, but it's in the negative territory. It's reflected in the x-axis. Okay. So here, if I'm going to use my recipe, I start with y is equal to x squared, and now I put this other domain restriction in, which says that x has to be less than or equal to 0. So now I'm doing the same thing over here, but now x is less than or equal to 0. So the next step says, okay, swap x and y. So wherever you see a y, make it an x, and vice versa. Where it's an x, make it a y. So now I get this restriction, x is equal to y squared, and y is less than or equal to 0. Now you can take the square root of both sides, but instead of getting two solutions, you get one unique solution here, because you know that y is less than or equal to 0. So you have to only get one possible value here. You can't keep with two solutions. If you get more than one solution, then the function's not one-to-one. You're actually finding more than one input that gives you the same output. Okay, but because we're restricted to this, restricted y like this, there's only one possible value for y. That's the negative square root of x. So the inverse of x is the negative square root of x, and that means, so the branch is going below the x-axis instead of above it because it's negative. All right. Great. So that is so new topic now. So let's just summarize what we've done. What we've done is we've talked about functions. We've talked about the domain and range of functions. We've talked about composition of functions. And we've talked about inverses. And we've given a way of actually getting an inverse. So now we're going to sort of apply these concepts to two special classes of functions, the exponential functions and the logarithmic functions. So let's do an example first. So anyone here have an accounting degree or anything like that? Or you don't need an accounting degree for this? No. I saw the roster, and it looks like most people have some sort of technical degree, like EE or computer science or physics or something like that. What? Or business? That's fine. All right, because this is completely unrealistic. So put $1 into the bank. Okay. And it's going to double. The bank has 100% APR. So your money is going to double every year. Okay. What is the balance after, say, 5 years? Okay. Computer scientists will know this like that. What?
2 to the 5th.
2 to the 5th, which is what?
32.
Thank you. 30. All right. So we can actually plot the size of the balance after year. So you're putting $1 in at year 0. So the balance after right at the present time, which is year 0, is $1. Multiply that by 2 for the next year, you get 2. Multiply that by 2, you get 4. And then doubling it each time, you get 8, 16. This is being really slow. Okay, 32. How about after 10 years? What should you have?
Which is 1024.
1024. Okay. All right, doubling each time. There's 1024. All right. Now, if we want to take an arbitrary number of years, call it x, then we'd like an expression for the amount of the account after x many years. So that is going to be, well, if x is, say, a positive integer, then what we are going to get is we're going to get 2 times 2 times 2 times 2 x many times. Okay. So, for instance, x equals 3, 8 is 2 times 2 times 2. For after 2 years, it's 2 times 2. And each successive year, we multiply by 2. So, as we know, this is an exponential. An exponential is an expression where you have one number to the power of another number. We write the second number as a superscript, and we call the superscript the exponent, and we call the bigger number the base. Thank you. All right. So you can do this essentially, well, for any two numbers. That's not entirely true. The exponent, the base. For the moment, the base has to be positive. Sometimes you can have negative bases for restricted exponents, but we're going to assume positive bases. So after x years, you're going to have 2 to the power x many dollars. So here's what we're interested in. We're interested in fixing a base like 2 and letting x be the variable. So x is the input variable, and what we're doing is we're taking 2 to the power of x. So notice this is different from the squaring function, where it was the base which was the variable, and we fixed the exponent to be 2. Here we're going to fix the base and let the exponent vary. All right. So fixing the base 2, this gives us a particular function of x. We call this the exponential function with base 2. So let's graph it, see what it looks like. Well, if x is equal to 0, we get 1. That's the balance. That's the current balance. After a year, we get 2. After 2 years, 4. After 3 years, 8, 16. So every time we take a step to the right, we go up twice as far as we did last time. So these points are going to give us, these points are going up very rapidly, exponentially fast. But we can actually extend this function into negative exponents. And the rule here is that if you've got $1 at year 0, what would you have had to have a year previous if you didn't make any deposits or withdrawals? If things are doubling each time, what did you have a year ago if you have $1 now? You had 50 cents. You had half a dollar. So 2 to the negative 1 should be 1/2. So this is true in general. If you take a to the power of negative 1, this is 1 over a. A now can't be 0. So 2 to the negative 1 is 1/2. So you get that point here. So we're extending the curve, we're extrapolating it in the left direction here. What about 2 to the negative 2? If x is negative 2, so if you have $1 now, how much did you have 2 years ago? You had a quarter. Okay. You can do that as follows. 2 to the negative 2, write negative 2 as 2 times negative 1. And then recall another basic fact about exponentials. If I take a to the m and take that to the n, with parentheses here, saying I take a to the m, and then I take that thing to the n, then it's the same as multiplying m and n together and taking that as a single exponent, and applying that to the base a. So a to the m times n, you can split that into two pieces, exponentiate with m first and then with n. And notice because m times n is the same as n times m, you can flip those. This is also the same as a to the n, all that to the m. So this is either way. Okay, so applying that here, this is 2 squared to the negative 1. Well, 2 squared is what? What is that? 4. And anything to the negative 1 is 1 over that thing. So that's 1/4, as we expected. So there's that 1/4 here. So you can do that for any number, negative integers as well, positive integers. But in fact, we can now interpolate these points, and the exponential function is defined for all real x. And it has to satisfy these facts for all real x. Okay. So exponential function of base 2 is actually defined for all real numbers x, not just integers. And what you're going to get is you're going to get values in between the values you see in this table here. All right. So a to the negative n, this is always 1 over a to the n, just applying these two rules together. Where just applying these two rules. A to the 0 is always going to be what? Always 1. Here's another rule which is useful, although I'm not going to use it on the slides. It's useful for a lot of different things. If I multiply two bases together and take that to the any power n, I can always do the same by taking a to the n power of n and multiplying that by b to the power of n. So an exponent, we say that the exponent distributes across a product of bases. So I can apply the exponent to each base and then multiply the results together. That's also true. Let's try this again, but instead of base 2, let's do a different base. Let's try base 3. So now the account triples every year. Starting with $1 again, currently. After a year, you're going to have $3. And then after 2 years, you're going to have $9. And then 27, and then what's the next one? Anyone? 81. Okay. 243, and so on. Okay. And after that, I don't remember. Okay. So now, after x years, the expression is 3 to the power x. So you multiply 3 by itself x times. If x is a positive integer, you can do that. And this is now called the exponential function with base 3. Okay, so let's graph this. Well, if you're tripling the money, you're going to get more money faster. So what we expect is these green points, which is going to be y equals 3 to the x. They're going to go up faster to the right than the red points. Okay. So in positive territory, I get 3, 9, and the next one is 27, which is off the page. So going into negative territory, 3 to the negative first is 1/3. So that point's down there. Now notice the green point is below the red point. So what happens if the base is higher? the green points are going to be farther up on the right, but they're going to be closer to 0 on the left. All right. What's 3 to the negative 2?
1/9.
Okay, 1/9. All right. And using this, it's 1 over 3 squared, which is 9. 1/9. All right. So we get this curve here. The green curve is y is equal to 3 to the power of x. So these are two examples of exponential functions, and that's what the graphs look like. Okay, it's very characteristic. It's a very unique shape for the graph. Okay. I've got some spurious animation going on in here. I do my best to fix these slides, but every time the slides are put on a new computer with some new updated version of Windows, something always goes wrong. And I apologize on behalf of Microsoft that this happened. All right. Okay, so let's do a general definition now. So I'm going to fix some value a, which has to be bigger than 0, but not equal to 1. Okay, so this includes all positive real numbers. So a does not have to be an integer like 2 or 3. It can be any real number, as long as it's not equal to 1 and it's positive. Then the function f of x equals a to the power of x is called the exponential function with base a. So there are infinitely many exponential functions, one for each choice of a. You get a whole new function. X here is this dummy variable, which describes the function for each a. All right. This function is increasing if a is bigger than 1. Increasing means that the curve is rising from left to right. So if a is bigger than 1, the function will be increasing. If a is less than 1, what happens? Let's get to the graph. So here's a base that's less than 1. It's 1/2. Okay? With g of x equals 1/2 to the x. Well, 1/2 is 2 to the negative 1, power of negative 1. Okay? And by our rule, this is equal to 2 to the product of those two things, which is 2 to the negative 1 times x, or 2 to the minus x. So what that graph is going to look like, well, we know what this graph looks like, right? We just have it. It's right over there. It's the red one. There it is again. Okay, so the scale is a little different here. That's 1, 2, 3, and these go up by 2, 2, 4, 6. Sorry, I got to step back from the camera. So this is what g of x looks like. I'm sorry. This is what 2 to the x looks like. Here is what 2 to the minus x looks like. It looks like this red line, which, notice this is just the pancake flip. It's the mirror image of the gray line in the y-axis. Okay, why is that? Well, it's because this function is really the composition of two things. It's first you apply the negation function, the function that negates its input. Then you apply g1 to that. So it's the composition of first you apply the negation function, then you apply this exponential function with base 2. Okay. What the negation function does is it effectively maps x to minus x. So it takes, if here's the origin right there, it takes x and maps it to minus x, which is on the other side of the origin, and vice versa. So it'll take this x and map it over there. So what it is effectively doing is it's swapping the x coordinate, across the origin. So it's effectively doing a horizontal reversal of the whole graph. So if you do that, if you take the gray graph and subject it to that horizontal reversal, you're going to get the right graph. This is a typical way of actually taking a basic exponential function and kind of massaging it into some other exponential function. Notice the red graph is decreasing. And that's true in general. So the exponential function is decreasing if the base is less than 1. So if it's between 0 and 1, you get a decreasing exponent. All of these functions have a horizontal asymptote. What's an asymptote?
It's line which the function isn't crossed.
Okay, it's a line that the function gets arbitrarily close to but doesn't touch. And each function has a horizontal asymptote, the line y equals 0, which is the same as the x-axis. So these lines get arbitrarily close to the x-axis, but they never touch. There are no other asymptotes, just this one. Okay. All these functions have a y-intercept. What's the y-intercept? It's the point where it crosses the y-axis. All right, so it's the y value you get when you plug in x equals what? 0. Okay, so when you plug in x equals 0, a to the 0 is always equal to 1, so the y-intercept is always 1. So these are always going to cross the y-axis at the point 1. All right. What's the domain? What do you think the domain is? Just by looking at it. All real numbers, yeah. So this is defined for all real numbers. There's no domain restriction on this. So that's minus infinity to plus infinity. What's the range? The range is the set of all outputs. All positive numbers, because you've got this horizontal asymptote, so these curves are going to get arbitrarily close to 0. So every positive number is actually going to be some output. Okay. Every horizontal line you draw above the x-axis is going to cross this curve somewhere. So the range is, in fact, all the positive numbers, but what about 0? Yeah, so this is never 0. So this never actually touches the x-axis. It gets arbitrarily close, it never touches. So 0 is not in the range. You could never have a to the x equals 0. That has no solution for x. So we exclude 0, and we denote that by the parenthesis instead of using a square bracket. Let's do a couple of these. I'm going to do some of these. I'm not going to do all of them. I'm going to skip over some. Let's sketch some graphs here, just to get. Remember, so we had this idea of actually flipping things horizontally to get different functions. Well, we're going to take that idea and run with it a little bit here. So let's look at f of x equals 5 to the power of x minus 1. Well, to get this graph, you can start with the basic exponential function, which is f1, f sub 1 of x. So this subscript has no significance other than I just want to choose a different name than f. So I'll just put a subscript on it. I could have called this g or h or anything. Okay, there's nothing significant about the subscript 1. Well, okay, so here's the exponential function 5 to the x. There it is, the gray line. But before I apply it, what do I do to x? I subtract 1. So this is actually going to correspond graphically to doing something horizontally before with the graph. So in fact, it means I'm going to shift the gray line over to the right by 1. Okay. Let's see if we can see why that's true. Oh, no, skip that. Okay, go back here. Well, the gray line was this function right here. Okay, so the gray line was 5 to the x. Well, what I'm doing here is first I'm taking x and subtracting 1. So if I take some x like equal 2 out here, in order to get the value of f, I would first subtract 1, so I'd go to the left by 1, and then I'd go up until I hit the gray line. Well, so if I want to do that, so the value I get by going over to the left by 1 and hitting the gray line should be the same value I get if I graph this thing as doing the same thing at 2. So the only way to do that is to shift the gray line over by 1 over to where 2 is. So when I go up from 2, I get the same value as if I had gone over to the left. So subtracting 1 from the exponent is equivalent to shifting this exponential function graph over to the right by 1. Okay. All right. So if you didn't follow that the first time around, we've got it on tape. So all right. Let's try something more complicated, and maybe I'll just do these. Okay. So 20 minus 5 to the power of x minus 1. Well, rewriting this just a little bit, this is negative 5 to the x minus 1 plus 20. Now what I'm going to do is I'm going to be doing a couple of different shifts and tweaks in succession. Excuse me. So this is the graph I actually get. And the first thing I do is, well, I can take this graph, which I've already got. I already got 5 to the x minus 1 is that red line. First thing I do is negate it. But now I'm composing with the negation function, so the negation comes afterwards, comes after the exponentiation. Any function you apply after the exponential corresponds to doing something vertically. Negating this means you're going to flip this curve vertically. You're going to flip it in the x-axis. So you're going to swap out an output y with negative y. Okay, so we're negating the output rather than the input to the exponential. So first we flip it vertically across the x-axis, so I would get a curve that goes like this. But then I add 20 to that output. Adding 20 means now I'm shifting the curve up, the whole curve up by 20 vertically. So that means instead of having 0 as a horizontal asymptote, I now have the line y is equal to 20 as a horizontal asymptote. So so from the very beginning, if I start with the gray line, I shift it over 1, flip it vertically in the x-axis, and then push it up by 20. And that gives me that red line right there. Do I want to do any more of these? No, not really. Yeah, I'll do one more. Okay. So because there's one more fundamental equality identity using exponentiation, exponentials. So what is this equal to? If I multiply two exponentials with the same base, it's important, the same base, what's that equivalent to? Yeah, not quite. You add the exponents. Okay, you don't multiply them. That's the thing is, this is a to the m plus n. Okay, so remember, there's a distinction here. So a to the m times, parentheses there. Can you all see this? ready for the trash. This is a to the m plus n. We had another one that had a to the m times n, but that was something else. That was a to the m to the n. That's the difference, okay? So don't get those two confused. So we can use that right here, in fact. So we're going to use the top thing over here, because this looks like the right-hand side. The exponent is the sum of two things. So this is 1 plus a negative x. So we can use this equation and write this as 5 to the power of 1 times 5 to the power of negative x. Well, start with the basic exponential here, which is 5 to the negative x, or if you like, 1/5 to the x. It's that gray line, because the base is 1/5. And now I'm going to multiply it by 5. So start with, see the gray line here? So now I'm multiplying the output by 5. So what do you think that does? Graphically, what does that do? Give me a word. It's going to stretch it. It's going to just elongate everything vertically by a factor of 5. So everything above the x-axis is going to go up, and everything below the x-axis is going to go down. So the whole thing gets stretched like an accordion by a factor of 5, and so when you do that, you get that. So here the y-intercept was 1, now the y-intercept is 5. Okay. Oops. All right, I'm going to leave that on there. Same f now. Exact same f, we're going to do it a different way. We're not going to use that formula up here. We're just going to take the basic exponential 5 to the x, and now we're going to do some horizontal stuff to take care of the exponent. So here's 5 to the x. Well, the thing you do right before the exponential is you add 1. Okay? So right before the exponential, you add 1. So how does this change the gray line? It moves it to the left by 1. So move to the left by 1. You get that black line. But then the very first thing you do, so now we're working backwards from the basic exponential. The very first thing you do is you negate the exponent x. So negating x does what? You're doing it before the exponential, so you're negating the input. So it's a horizontal flip. So it's a flip around the y-axis. So that's what you do when you flip around the y-axis. And if I don't have it here because of the animation, unfortunately, but that red curve is exactly the same red curve we got the other method. So sometimes there's more than one correct way of doing this. All right. But I don't want to dwell on this. For one thing, I'm way past the break and no one's reminded me. So. All right. I know you were just so enthralled by what I was saying.
It's my fault.
All right, 10 minutes.
Didn't set up, you know, with his name on it.
Yes, I will.
All right. So we're back. If you're following this at home, I skipped over a few slides. And so I'm just going to do one more example of this, and this will be number E. So, again, using a base of 5. Let's try f of x. I was graphing this. F of x is 5 to the power of x over 3 minus 2. So now, all the shifts and things are going to happen with the exponent, so they're happening before you apply the exponential function. So they're going to be horizontal things versus vertical things. So this is 1/3 times x plus a negative 2. So let's just recall our things here. So this is 5 to the 1/3 of x times 5 to the negative 2. So that's rewriting this using this one up here. That's 5 to the 1/3, all that to the power of x, times 1/25. Okay. So actually, I lied to you. What we're going to be doing is doing this. We're going to take this as our base, 5 to the 1/3, which is a real number, and taking its exponential to the x, and then multiplying the result, multiplying the output by 1/25. So the other rule a to the 1/n is the nth root of a. Okay, so 5 to the 1/3 is the cubed root of 5. In particular, a to the 1/2 is the square root of a, and for the square root, we can leave off that number there. Okay, it's 2 by default. All right. So here we've got the cubed root of 5 to the power of x, and then we multiply the output of that by 1/25. So we start with this exponential function, and the base is now the cubed root of 5, which is approximately equal to 1.7. So that squiggly equal sign means approximately equal to. So there it is. There's the gray line. We take that, and now we multiply the output by 1/25. Now 1/25 is much less than 1, so what we're doing is we're doing a vertical squeeze instead of a stretch. We're doing a vertical squeeze by a factor of 1/25. So we're pushing everything toward the x-axis from above and below. So this gray line gets pushed down to the red line. And now the y-intercept is going to be what? The red line. What's the y-intercept? The gray line, the y-intercept is 1, and so the y-intercept for the red line is 1/25. Right. 1/25. Or 0.04. Oops. All right. Okay, so yeah, that was the only example I want to give. In the slides, we use the squiggle equals to mean approximately equal to. In the book, I use an equal sign with a dot over it to mean the same thing. Okay. So they both mean the same thing. They're interchangeable.